start with state transition matrix. So, what is meant by state transition matrix? If you see a classical system, the classical system, there is involvement of a plant, say G of S. We are applying input and we are getting output. So, input is applied at t equals to 0 and we are expecting the output at certain time interval, say output say at say t equals to say 10 second. Now, this is a step input and now this is the output. So, here output we have got at t equals to 10 second. But in case of state space system, along with this output there are states which are the important parameter in the system that has been also travelled, that is from t equals to 0 to t equals to f, the state has been transferred. So, this transferring of the states we can say that state transition matrix. Now, how will you define the state transition matrix? It is defined as the transition of states from initial time t naught to any time t or final time tf when the inputs are 0. That is, this state transition matrix is not concerned with the any type of input. It is concerned with the some initial state, that is t0 to tf. Now, we will see what are the significant, what are the importance of this state transition matrix. The first point, it is defined as the solution of linear homogeneous state equations. We have seen last time the x dot equal to x, x of t equal to e raised to a t x naught. So, this is e raised to a t is called state transition matrix and this is homogeneous state equations. It is a response due to initial vector x naught. It is a response due to initial vector x naught. Here this is what. But if you consider a force system like this, x dot equals to ax plus bu. So, here we will get x of t equal to e raised to a t x naught plus 0 to t, some values will get here, coefficient will get, and we get d of t. So, in this particular case this is e of t, it has been taken care by x naught only, whereas if you take this part, this portion, that is a force portion, force part, in this particular part there is no involvement of x naught. So, therefore, what we are saying here, it is dependent on the initial state vector, not the input. The input is concerned with the force part only. This part state transition matrix is concerned with only x naught. So, it is called as 0 input response, sin input is 0, and whereas if you take the force part, this is called as 0 state response. Here in this particular force part there is no initial state has been involved, but as far as now we are discussing about the state transition matrix, it is concerned with the 0 input response, because this portion e raised to a t into x naught, this portion there is no input. It is called as a free response of the system, since the response is excited by the initial condition only, that is due to initial conditions the state has been transferred, and that is called state transition matrix. Now, we have to see few properties of this state transition matrix. Say phi of t equal to e raised to a t, that is a state transition matrix, and now we have to prove this phi of 0 equal to I. This is first part, first property. So, how will you get I? Identity matrix. So, in these particular equations, that is phi of 0, we replace, we will get identity matrix. Now, the second properties, we have to prove phi of minus t equal to phi of minus t, that is phi inverse of minus t equal to phi of minus t. Now, how will you prove this one? So, now we start with the same equation, phi of t equal to e raised to a t. Now, through this equation we now post multiply by e raised to minus t, that is what we have to do. To this equation we have to post multiply by e raised to minus a t. So, after post multiplication what we will get? We will get phi of t to e raised to minus a t equal to e raised to a t into e raised to minus a t. This is post multiplications, that is phi of t multiplied by e raised to minus a t, here e raised to a t multiplied by e raised to minus a t, we will get identity matrix. Now, our main purpose is to get phi inverse of t equal to phi of minus t. Now, what will you do? We will pre multiply both sides by phi inverse of t. So, what will get? So, if you multiply this phi inverse of t into phi of t to e of e raised to minus a t, so phi inverse of t, that is I. So, this is cancelled, what will get? E raised to minus a t equals to phi inverse of t. So, e raised to minus a t equals to phi inverse of t. Now, this if take phi of minus t equal to e raised to minus a t, just like phi of t equals to e raised to plus a t, but if you say phi of minus t equal to e raised to minus a t. Now, if you see this equation, say 1, you can say this equation 2, if you compare these equations, so what we will get? We will get phi of phi inverse t equals to phi of minus t. This is a second property. Now, we see the another property, the another property is phi of t2 minus t1 phi of t1 minus t0, that is equal to phi of t2 minus t0, phi of t2 minus t1 phi of t1 minus 0 equal to phi of t2 minus t0. Now, this we can express through a diagram. Now, here one point, this one, another point here. Now, here x of t0, and now here is x of t1. Now, the state has been transferred from x of t0 to t1. So, that has been represented by a phi of t1 minus t0. Then same state, now we see take x of t2 to t2. Now, here also the state has been transformed from x of t1 to x of t2. So, it has been represented by phi of t2 minus t1. Now, you just see this phi of t2 minus t1, phi of t1 minus t0 equals to phi t2 minus t0, that is this particular portion, phi of t2 minus t0. Now, we have to prove this part mathematically. How will you prove this? So, here phi of t2 minus t1 phi of t1 minus t0. Now we have to solve this. So this is also a transition matrix, state transition matrix. So it has been represented by e raised to a t2 minus t1. You see this portion, this part, and about this phi of t1 minus t0, it has been written by a of t1 minus t0. Now we solve this one. So we can write down as a of e of a t2 to a of minus a into t1, that is multiplications, e of a into t1 multiplied by minus a into t naught. Now you see here e of minus a t1 minus a t1, this will be cancelled. So what we will get? E of a t2 minus t0, and that is nothing but phi of t2 minus t0. Now we have proved this part. So here transition of state from t0 to t1, t1 to t2, but it may possible that the state at x equal to t2 may transfer to x equals to say t3, that means x equal to t3, that is it can be represented by phi of t3 minus t2. Now how do you express this through state transition matrices? That is phi of t3 minus t2, phi of t2 minus t1, phi of t1 minus t naught, that is equal to phi of t3 minus t naught. That is, you see here phi of t3 minus t2, this one, phi of t2 minus t1, then phi of t1 minus t0, and this is a complete part, there is the involvement of phi of t3 minus t naught. So similarly, more state elements we can add it, and we can express this in terms of state transition matrix. Now the next properties, say phi of t, say raised to m, equal to phi of m into t. So in this case m is any positive integer. Now this we have to prove. So now this phi of t raised to m, so phi of t is nothing but e raised to at. Let us say m equals to 2, that means e raised to at multiplied by e raised to at. Now here m is there, that means e raised to at has been written in terms of m times. Therefore this equation we can write down as e raised to at multiplied by e raised to at, e raised to at up to e raised to at. Now up to how much terms we have to write? This we have to write m times. See here f phi of t raised to m, e raised to at, e raised to at, m times. So this we can write down as e, how much time is m into a into t, m into a into t, and now we seen that this x t equals to e raised to t x naught. So this is written as phi of t. So here this can be written as phi of m into t. Here m term has been added, therefore this result has been proved. So these are the properties of the state transition matrix. Sometimes when we are doing the analysis of the system and many states are involved, this type of properties can be useful. Now the point has come, this e raised to it is there, that means whenever we require state transition matrix we have to calculate e raised to at. Now how to calculate it? So if you see the literature, there are various methods are available. So these methods are useful to calculate the state transition matrix. Now we will see the various methods. for determination of state transition matrix. So, first one is power series method, Laplace transform method, diagonalization method and Cayley-Hamilton method. So, these 4 methods can useful to get the state transition matrix. If you take any example, then apply this 4 method, you will get the same results, but now which method to be applied. So, this depends upon the type of systems. If you see the power series method, we will see it, but we will find that as the order increases, calculation is quite difficult, and sometimes we do not know whether we will get result or not. This Laplace transform method is based on S domain, and Laplace is very important tool. Therefore, we will find that the Laplace transform method is quite useful. We have already seen this approach earlier to get the state equation, that is x dot equals to Ax, x of t equal to e raised to at into x naught, and now this phi of t equal to e raised to at equals to Laplace inverse of Si minus A inverse. By means of this, we can calculate this state transition matrix using Laplace transform method, that is you have to take Si minus A inverse. Now, the diagonalization method, this method is based on the concept of converting the given system matrix into the diagonal form, and in this case there is need to go for the model matrix. So, if you see it, the calculation wise this method is quite cumbersome, but Laplace transform is quite better. Now, next is Cayley-Hamilton theorem. This is a very important theorem and it has wide applications. So, we will find that this method is also useful in getting the state transition matrix. Now, we will see this method we have already seen, only the method which we have to see power, diagonalization and Cayley-Hamilton theorem. Now, we start with power series method. So, here we start with x dot equal to Ax, or this we can write down as x dot t equal to A into x of t, and here x of t state equation equal to e raised to at into x naught, and here this e raised to at that is equal to I a into t, a square into t square factorial 2 plus a cube t cube factorial 3 and this process method. Now, we have to prove this, why the state transition matrix e raised to at equals to this way. Now, we start doing it. So, first of all what we will do, we will assume that say x of t equal to C0 plus C1t plus C2t square plus say Ck into t to k x of t. Now, we are concerned with the x dot t. So, here x dot t equal to A into x of t. Now, if you see x dot t, so now differentiate these equations. So, if you differentiate x dot t, this term of C0 will not present. So, terms of C1, C2 up to Ck will be present. Therefore, we write the equation as this is C1 plus this differentiation of this 2 into C22, 2 into C22 into t plus 3 C3 into t square, and this process repeated, that is here C3 is there. So, here C3 t cube means 3 C3 into t square equal to A into x of t. So, we can write down as A into x0 C0 C1t C2t square like this, or we can write C3 t cube. So, these terms we have got, and now our main purpose is to get this result. So, what we can do? Means in what way we proceed? So, we can see that we can compare the various terms of t and somewhere we can achieve the result. So, please see it. So, now what we will do? Comparing the coefficients of t. Now, we compare the coefficient of t. So, now see here, for if see the term t raised to 0. So, we will find that t raised to 0 means 1. So, here for this it is C1 and here is A into C naught. Similarly, we compare the terms t raised to 1. So, here that is t. So, we can write down as here t raised to 1 2C2. So, 2C2. Now, here we will find A into C1 into t, this here A1 C1 into t. So, we can write down as A into C1. So, from this we can write down as C2 equal to A by 2 into C1, C2 equals to A by 2 into C1. No, but we know C1. What is C1? The C1 is A into C naught. So, we replace the value of C1 in this equation. So, we will get C2 equal to A by 2 into A into C naught equal to A square by 2. So, we can write down as a factorial 2 into C naught. So, why I write factorial we will see later on. Now, here we have compared the coefficient of T1. Now, similarly we have to compare the coefficient of T2. So, if you compare the coefficient of T2, we will get 3C3 into A into C2. So, here 3C3 into A. Now, 3C3 into A, what is C2? C2 we have already got A square factorial 2 into C naught. So, we replace these values here. So, we can write A square by 2 into C naught. Now, we got A square by 2 C naught, but we know also C naught. So, C naught is, so you will find that C naught is no value. So, we can keep like this only. So, we can write down as this C3 equal to 3 will take this side and we will get A cube into C naught. So, here we can write down this as 6 into A3 into C naught, and if you write this as factorial 3, that is 3 into 2 is 6, A cube into C naught. Now, similarly we have to proceed further. Suppose if you replace t equals to 0 in the equation of x of t, that is x of t equals to C0 C1t C2t square plus Ck into Tk. So, you will get x of 0 equal to C naught. So, now we have got the value of x naught, C0, C1, C2, C3, assume that we got up to Ck. Now, we replace all these elements in the given equations, and now we will see what results we will get. That is x of t equal to C0 C1t plus C2t square up to Ck into Tk. So, we have got all values of C0, C1, C2 into Ck into Tk. So, you can also find this process A equals to C0, C1, C2 into C3 into T cube, this portion, and we got all values, and now we try to replace. So, if you replace it C0, what is the value of C1? C1 you will find, you get C1 equals to A into C naught, C2 equals to A square factorial into C naught, and C3 equal to 1 by factorial 3 AQ into C naught. So, we replace these values and we will find C0 into A into C0 into T plus C2 A square factorial 2 C0 into T square plus A cube factorial 3 C0 into T cube, and this process repeated, and we will find that this is 3, our terms are up to k. So, we will have 1 by factorial k into a raised to 3, so k. So, we will have a raised to k into t raised to k. Now, we will find that in all these cases, the term C0 is common. So, we will take C0. So, we can write down I plus A into T, A square factorial 2 into T square, A cube factorial 3 into T cube plus 1 by factorial k A raised to k into T k. So, now we have got this one. Now, what is x of t? So, x of t is equal to e raised to at into x naught, and what is x naught? This x naught we have already calculated as c naught, and therefore, this e raised to at into c naught, and therefore, if you compare this equation, this is the same equation. Now, here e raised to at is nothing but this part, that means we can write down e raised to at equal to I plus a into t plus a square t square factorial 2 plus a cube t cube factorial 3, and like this a k t k factorial k. Now, this is the direct formula. So, by means of this formula we can easily get the state transition matrix. So, in that case, what is the input is available to you? Input is available to is A matrix. So, you replace the A matrix and solve it, you can get the result. Now, we try to solve one example. Suppose if you are taking A matrix equal to minus 2 1 0 minus 2, and we want to determine, we have to determine the state transition matrix e raised to at by means of power series approach. So, here e raised to at equal to same formula we have to use I a into t plus a square t square factorial 2, and like this. Now, here we will find that we will get a square a cube. It means that we have to calculate many multiplications, multiple multiplication has to be solved, and we will find that to do these calculations or to carry out this calculation sometimes is quite cumbersome. Just we will see here, suppose if you take a is like this, same thing, minus 2 1 0 minus 2. Now, we have to determine a square. So, a square is minus 2 1 0 minus 2, here minus 2 1 0 minus 2, and if you solve this one you will get 4 minus 4 0 into 4, and we got a square. Similarly, you can get a cube equals to a into a square. So, we have to solve, you will get some values, and finally, you have to replace in this particular equations. So, you will find that there are some terms. So, everywhere these terms are added, and finally, if you get e raised to at as e raised to minus 2t, t into e raised to minus 2t 0 e raised to minus 2t. That means, what you do? You have to determine a square, a cube, a 4 like this, they replace these values, and from this same expression taking different elements we will get e raised to minus 2t, that is e raised to minus 2t portion is nothing but 1 plus minus 2t plus 1 plus factorial 2 minus 2t square plus factorial 3 minus 2t whole cube. This is e raised to minus 2t. Similarly, we will get t e raised to minus 2 to t 0 e raised to minus 2t. So, this is very simple calculations, you can easily do it, but here the main intention of this example is that sometimes it may not possible that you can get similar type of results, that is instead of minus 2 sometimes we will get 4, it may get 7. In that case, to make these elements or adjust this element by means of power series expansion is quite difficult. Therefore, as we increase the order, we will not recommend this method to get the state transition matrix, because calculation is quite difficult. Therefore, in that case it is better to go for the Laplace transform approach, or there are other approaches, that is called Cayley-Hamilton theorem or diagonalization, that are also helpful, but this approach sometimes is quite difficult. Now, you see the references Gopal Tira Chaudhary, Ku Verma, and so these references you can use, or you try to solve many example as possible using these power series expansions, and as I told you that you identify in the various cases where this method fails, and the same problem you can solve by a Laplace transform approach, and you prove that Laplace transform is better than the power series method. Thank you.